So far we've discussed the impulse momentum theorem, where we apply a force during a duration to an object in order to change its momentum, which is a measure of a movement of an object with a given mass. Now we're going to look at how momentum is conserved in a system of objects if there are no outside forces on an object. First of all, let's define what we mean by a system of objects. If we have a ball and they're flying, maybe these are pool balls, and they run into each other and they bounce off, each of them is going to have a mass and an initial velocity and after they run into each other and bounce off, they're going to have a final velocity. So these two pool balls are our system. So a system is a collection of objects that we're interested in tracking during a problem. They are usually going to be interacting with one another. They might be interacting with something else. Anything else they interact with, we consider the environment. And we want to figure out what happens to them from the beginning of the problem to the end of the problem. Now, when we're talking about conservation of momentum, what we hope to happen is that they don't interact with an environment. So first of all, we can define what we want for the what we mean by the total momentum of the system. So notice here we have an m1 and an m2, and we have their initial momentum, initial and final velocities. So for each one, we can define an initial momentum for object 1 and an initial momentum for object 2 and so forth, and a final for object 1 and a final for object 2. Sometimes I get my subscripts backwards. It doesn't particularly matter as long as you can keep track of which thing is which. Now, if we take all of our objects in a system and add all their momenta together as vectors, so even in one dimension, if we just have the x direction, keep track of the pluses and minuses, right? So if we add them together as vectors, then that total is our total momentum for our system. So in particular, we would have an initial, which would be P1i and P2i, and we would have a final, which would be equal to P1f plus P2f. Notice that these are meant to be capital P's and these are meant to be lowercase p's. That's how we denote those. So when we have a conservation of momentum, we're usually talking about our system of objects. And just like for an individual object, if we have external forces, we can change the momentum of that system. And that would change due to an impulse. But let's say those external forces either cancel out or there are no external forces, then that external impulse is going to be equal to 0. Well, then that means that our change in momentum is going to be equal to 0. This is for our whole system. And then that means that our final minus initial 0, that means our final is equal to our initial, and that means that we can start plugging in our original little p's, and then we can even multiply them out. This is what we mean by conservation of momentum. Really, any of these lines, but this is where we can particularly apply it to a physics problem. When we add up the momenta of all the objects, again, as vectors, the initial is equal to the final. And what typically happens is that we have information for everything but one of these values, right? And so we're going to look at two main types of scenarios in conservation momentum problems, and those are going to be collisions, where things come together, and explosions, where things come apart. So, our first example. You have a cousin on a longboard. Cousin on the longboard is initially stationary. And you are running up and you jump on the longboard so that together you are riding off safely without harm together. Okay? This is what we find out. Again, the most important thing about this kind of problem is that you want to define your coordinate system and then maintain all vectors, the positives and minuses, relative to that coordinate system. So what kinds of things do we know? Let's call you M1 and cousin will be M2. So you have an initial VI. First of all, we have M1 is equal to 80 kilograms. And V1I is equal to 3.00 meters per second. M2, we know, is 50.0 kilograms. And V2I is equal to 0 meters per second because your cousin's standing on the longboard. And what we're trying to find is VF, right? Here's the thing. Whatever VF is, it's the same for both of you. So V1F is equal to V2F, and we could just call both of those plain old VF. So what we're going to do in order to solve this problem, I would like you in my class to still always write down M1 V1I plus M2 V2I equals M1 V2F plus, get the subscripts right, E2F, right? So what you're saying here is PI is equal to PF, and then this is the most general statement that you can make about that. And then we can begin eliminating things, right? So we know that this is equal to 0, and we know that these two are the same. So we can say M1 V1I is equal to M1 plus M2 VF. We're trying to find VF. So we can have M1 V1I over M1 plus M2. Now we can plug in all the quantities, and we get 80.0 kilograms over 130.0 kilograms times 3.00 meters per second, and we get 1.85 meters per second. Okay, so this is an example of a collision. Specifically, this is called an inelastic collision, which is when the two objects that are colliding stick together. We will talk more about that next time. And then we have an explosion. Now, an explosion technically just means when two or more objects come apart due to internal forces. So it could literally mean, boom, sparks, fire, etc., explosion. Or it could mean you have, a spring separating two things that were stuck together with magnets or something, right? So it doesn't have to be explosions and fireworks, but sometimes it is. So the example we're going to do here is a bottle rocket of the type with pressurized air and a water propellant. you're already on YouTube. So just look one of those up. So we are going to have a water bottle. And it is going to be filled with water. Not filled, actually, it doesn't work if it's filled. Partially filled up with water. And, there'll be a nose cone and whatnot. And remember that we have to define our coordinate system. So we're going to say up is the positive y direction. And this is going to be our before, and our after is going to be the bottle is going to be flying upward, zoom, and the water is going to be flying downward, zoom. Okay, so let's define our values. So M1 will be the bottle, so that's 0.100 kilograms. M2 will be the water, 2.00 kilograms. And V1I is equal to V2I is equal to 0 meters per second because they are both stationary on the ground when you set this thing off. Now, the question is intending to find what is the velocity of the bottle after the water is propelled. So we're trying to find V1F. So we're going to use V2F. Now this is where the coordinate system comes in. It is being expelled at 10 meters per second. So when we use our coordinate system, this is being expelled downward, so this is a negative 10 meters per second. I should have put 3 sig figs there, and I didn't. We'll pretend I did. Okay, so let's put this all together. We're going to still use our PI is equal to PF, and so we have M1V1I plus M2V2I equals M1V1F plus M2V2F. The whole left side is equal to 0 because both the VI's are equal to 0. And so we have V1F is equal to negative M2V2F over M1. We know all those numbers. So we have a negative 2.00 kilograms times a negative 10.0 meters per second over 0.100 kilograms. And we get the negative and negative cancel out, and we get the shockingly large value of 200 meters per second. And now we ask whether this was ever a reasonable thing to calculate. And this is the key thing. It probably wasn't that reasonable to calculate. Because there's some external forces, aren't there? During the duration which this water is expelled, gravity and drag both have a significant effect, particularly when this is trying to get up to speeds of 200 meters per second. The bottle rocket is going very fast. It has a low mass and for its mass, a large cross-sectional area. And so because of all of those factors, J is not 0. It's not that close to 0. But this gives us some way to estimate, something about how its momentum could change. And if you put this into space, if you put a water-based rocket into space, this is how fast it could go if it, didn't blow up instead.